Brawley, California, apparently. Earthquake time.
But the water's going. Yeah. You should have it in the broken glass. There's about a foot of water, more than a foot of water out of the pool. Probably better go turn the motor off.
Who was in the Northeast for the 2011 Mineral Springs earthquake? Yeah. In your lifetime, for sure. So I remember being in my office and wondering what this low frequency vibration was. I think this isn't as spectacular as the Brawley one, California, bigger events, but this was magnitude high fives, I think, maybe six. In Mineral Springs, Virginia. It had the monument in the Capitol in D.C. shut down for some time. It knocked some stuff off the National Cathedral in D.C. also, some of the stonework, but I guess pretty mild here. It's not showing very much. So we're talking about accelerations today in static fluids. I said before that it was kind of a oxymoron, or moronic term. It requires that to get this behavior that you see in swimming pools, it requires that the period of the shaking has to be in line with the natural resonance of the body of water. And so that's related to the size of the swimming pool. In the same way that we get super big tides in places like the Bay of Fundy and the English Channel, when all the tidal forcing worldwide is the same, every 6 hours peak tide, every 6 hours low tide. And so you'd expect that the tide magnitudes would be the same everywhere, but they're not, because they're amplified in certain areas. And the way that they're amplified is you can think of the time it takes from water to go from the mouth of the Bay of Fundy up near above Maine to the top of the Bay of Fundy has to be on the order of the forcing, which is 6 hours up and 6 hours down. And if it's directly in concert with that forcing, then you get a much bigger tide. So tides, I don't know what the average tide is worldwide, it's probably a few feet, but Bay of Fundy is probably 30 feet. English Channel near Bristol in the UK is about the same. So it's amplified by the circumstance. And the Hebgen Lake earthquake was an earthquake that occurred in 1959, unfortunately dropped the side of a mountain on a campground. This is becoming the disaster class. I only know because I went there 30 years ago and saw this. And it had a sesh in the lake. And the lake is a long lake, and the period of the earthquake put in motion a sesh, a wave that went up and down the length of the lake a few times, or for a couple of days, I don't know how long, but because it was actually the forcing was exactly in resonance with the shape of the pool. And so in this particular case, I guess I lost the previous one. It wasn't very pronounced for the Mineral Springs earthquake, but the resonance of the pool is related to that. And we knew from maybe our second class that we had that the celerity wave, the surface wave, travels at the depth of the water divided by the acceleration due to gravity, right? That's the surprising rate that tsunamis travel at, maybe 100 meters a second. And if you looked at the recordings, extra credits for 1.2 or 1.3, then you'd have seen the example of the East Japan earthquake in 2011, actually also the same as the Mineral Springs earthquake in Virginia. And that was that it took 20 minutes for the tsunami, the celerity wave, to come from the trench where the earthquake occurred. Two plates went up against each other. One plate boundary went up maybe by 100 meters and then increased the water level above that part, but not above it. And that was the motivation of the tsunami to initiate. And then it came ashore 20 minutes later. And so that's kind of accelerating fluid. So that's kind of what we're talking about today, but not completely. The most obvious indication of what we'll talk about today is this. and it runs for a while. Perhaps I'll turn it down. And I said last time as we split, it's kind of a misnomer, or it's oxymoronic, that you can have accelerating fluids when you're talking about static fluids. And so they seem to contradict each other. But what we're talking about is fluids which are static in a box, but that box is migrating and not just going with some velocity, but going with some acceleration. And so this is a fortuitous capture of water between two panes of glass in a bus. And as the bus goes down the road, that elevation of that canters over. As you accelerate, it cants over. As you decelerate, it does the opposite. And so you could, if you wanted to, measure the acceleration of this bus just by looking at the slope of that component. So that's what we'll talk about today. We did kind of introduce it earlier because we made the point, I think I made the point, or tried to make the point, that you'll remember that we looked at these cars. I don't see a clear one. This looks like one. Can't really see it. But we made the point that these cylindrical cars aren't just cylinders, but they go up at either end. And that is because railway cars that carry fluids, Bakken oil perhaps from the Dakotas to the East Coast, accelerate when the train starts and decelerate when the train stops. And if you fill it up to the brim and have just flat cylindrical components, you'll pop the top off, you'll pop the lid off by the pressures that you develop, just by looking at the same kind of behaviors that we talk about in that bus. So the bus, as it accelerates, the back of the fluid comes up, and so that means that it will exert some fluid pressure if the lid was at the back of the train. If it comes up enough, it would also affect the lid that's halfway down the train as well. And when it stops, you get the opposite effect. And so that's what we'll talk about today. Okay? So hopefully you weren't perturbed by, switching gears, you weren't perturbed by the email that came out at midnight on Saturday, right? So the exam is not now today. So that was my snafu, so I apologize for that. But that same email, I guess if I'd have changed it to be week 5 and put the review session in it, would have been absolutely correct for this coming a week today. So the material is online. If you haven't looked at it already, you can find the review material online as a video. That is here. And with my sonorous voice. Doesn't have a voice on it? Should have a voice. Why doesn't it have a voice? Well, I'll check that. It certainly should have a voice. Anyway, I will make sure that that's the case today. This is the outline for the test. You see the material that's on it. It covers everything up to the end of today. Hopefully we'll get through stuff today through 4.1. To give you a break, I'm getting soft in my old age. And actually, we always give you a heads up on what the questions are. You see them there Monday, Wednesday, and Friday. Viscosity, pressure on planar structures, and accelerating fluids. I guess I turned it down. That's why I can't hear it.
401. You've been in those classes.
So you don't need to hear that. And so it gives you all the material you need in this review session. This equation sheet is what you'll get on the day of the test as well. I'll print it off on double-sided paper and give you that so you have that as well. And you'll see that it refers to the 3 topics there. And so if you go through this, you'll see what is we focus on in the test. Cuts you a break so you don't have to cover everything that we've covered in the first 3.33 weeks till today. I guess the other gift to you, actually, you can view it either as a gift or as me. I'm old. I'm almost dead. I'm almost 100. I can't make up new questions for you every exam. So these will be retreads. And so if I were you and I was getting ready for this and wanted to show, as an opportunity to show your immense skill in this area, then I would go through the prior tests, questions that relate to these individual topics. And I don't think you have to and go through it however you want to go through it. I would go through it by looking at the questions, thinking, how would I solve this? Writing down an equation and seeing how it was solved, because you have the solutions to all of these as well, and go through it like that. And so I would encourage, that's the way I would go about it. The other gift to you is that these are retreads. And so they're not verbatim questions, but they're pretty close to verbatim with some numbers changed around and made specifically for this format that we have, starting 30 minutes, 8 o'clock till 8:30, which is really probably 7:55 to 8:31 in class. And you can see the format of those tests. It's maybe 8 or 10 questions on a two-sided sheet. Write the numbers in the box. No extra credit for working, but questions that are designed so they aren't as follow-on as they could be in days past. So, never a fun thing to talk about these assessments. Though, of course, if you're a glass half full person, then you can think of it as being able to show your best. Yes.
So, like, how's the exam format there? You know, like multiple questions separately.
Yeah. Did you download the tests from online?
No, I didn't.
You should do. Okay. There are multiple questions in a single test, maybe 8 to 10, as I just said, with a single answer. Some are multiple choice, not by A, B, C, or D, but by giving you the choice of 5 numbers after the question. Put the numbers in. So, have a look at the stuff. It's not so daunting. Yeah, it's a chance to be able to show everything you know. Any other questions? Did anyone get any angst on Sunday morning? No, you're up too late. That's right. That's good. There were people up, night owls, I guess, at 2 o'clock in the morning. Said, "What the hell's this?" Yes.
If we get her earlier, could we start earlier?
7:55, probably. Okay. Right. So, and as you can see from that, what we'll talk about today is going to be the Friday question, I guess, right? So, special ears today, right? Any other questions? Okay. Yeah. It's necessary part of, I think, of what we're doing here. Okay. So and I can talk again at the end of class if you have some time. So we're talking about this misnomer of accelerating static fluids. And if you looked at the material for our Labor Day vacation, 2/1 it was, right? The Monday after Labor Day. You'll recognize the following. What we did, and I'll just reiterate, just to kind of set the stage. We won't repeat the derivation. But we talked about defining the equations of motion. And you'd have seen this little figure before. And it all seems a little horrible because it's differential calculus. But actually, it's no different to the way we framed it on Friday, in that we talk about this right-handed coordinate system, z positive upwards. Lengths of this cube were dx, dz, and dy. Doesn't matter. We had a weight of this cube was equal to mass times gravity, which is the same as volume times density times gravity. And we had pressures acting on the base. And we had a pressure acting on the top. and that pressure was P plus dP, and we multiplied that by dz. So this is 1, and we resolved this, and we also put on this accelerations, potential accelerations. We could accelerate by some acceleration in the z direction. We could accelerate by some acceleration in the y direction. And of course, me scooting across the floor holding one of your beakers of water, and it would be exactly that, a bucket with accelerating, but that contains the fluid. And the other thing that kind of related to this was this other picture we drew, which is perhaps much less intimidating, and that was that we talked about I didn't want to do that. We talked about calculating using paint cans on top of each other. I'll leave it at that. The fact that if we looked at pressure with depth, this is minus C, then we knew that we could get that pressure by just doing this. P equals P0 plus rho G H. This is P0. This is H. And this is the pressure at that point. So we can cast it in the way on the left, which is really just the way on the right, where the pressures that are acting on the faces of this differential cube matter on the fluids that are above us and nominally below us. Not really actually above us more than below us, because we have gravity acting downwards. And as a result of doing a little derivation with this expression, we ended up with these equations here. And these equations here came out of F equals ma. So there's some terms on the left-hand side that represent the sum of the forces. This is the only equation we need in this class, Newton's second law. There are forces in the x, y, and z directions, which each of these equations represent, which I'll write out in a minute. There's accelerations in each of the x, y, and z directions, and they're represented by this. And if we divide this through by the volume of this thing, which is just equal to dx, dy, dz, right? The edges of this differential cube, then we can divide both sides by the volume. So mass per unit volume is a density. Acceleration in x, y, and z is this. And all these other terms are the other forces that are applied on this differential cube. And so what we did, and don't do this, but we assumed that we would make our life easy in the first 3 weeks by setting all accelerations to 0. And if we did that, the equations that we got out of it would be this and this. So let me write these equations out for us. I'm going to make it small so they can both stay on the page at the same time. So I'll look, so that's too big, right? So in resolving in the x direction, dp dx minus gamma times 0, I think it's minus dpx, minus 0 times rho g is equal to plus rho times acceleration in x. We have in the y direction dp dy minus 0 times density of water, not P. Density of water times gravity equals density of water, of the fluid, times this acceleration in the y direction. And we have the rate change of pressure in the z direction minus one times rho g equals rho az. So the ones that we use, so this is summing forces in the x direction equals 0, summing forces in the y direction equals 0, summing forces in the z direction equals 0. And the expressions we got out of here is that if these are zeros, then we have dp dx equals 0, should be partial, dp dy equals 0, again should be partial, I don't know why I slip into this, and dp dz is equal to minus rho g equals minus unit weight. And we've used all of these. These are the ones that say if you go horizontally within a fluid, the pressure doesn't change. And we use that for the capillary tube going outside from atmospheric pressure, up inside the capillary tube. You can cut the capillary tube off at the bottom because it has to be the same pressure. So that's where that comes from. And this is where we get this from. This is just dp dz equals minus unit weight. We write both sides by dz. We integrate, and we end up with this. So that's where we are. So we've seen this before. So that's the background of where it comes from. It comes from nothing other than Newton's second law. So now we want to take care of the fact that we allow for these terms to exist. So if we do that, then we end up with, what would we end up with? I'm running out of space at the end. So if I take this one here, actually I don't want to do that. I want to use, the book uses y as an example. So I'm going to do it to this one. We get dp dy equals minus rho ay. And if we take the other one, we get dp dz equals rho g, taken to the other side. And there's a minus, choose one side to go on, and it's this. So those are the two equations that we'd like to mess around with. And the reason that we'd like to mess around with them is that they say something about what's going to happen within a container. And we could think of a closed container. And so a closed container can be your beaker, or it could be me running across the room with an aquarium full of water. And what we're going to do with this aquarium is we're going to decide on some coordinates. Z, and we'll use y rather than x. And so if we run across the front of the classroom in the y direction, accelerating, I guess it's the opposite direction, accelerating in this direction according to that on the screen. And then we'd expect that the pressure on the bottom, if it's not accelerating, right, it would be here, whatever the height of the water times P is equal to rho g h. H would be the depth downwards. And so the pressure here would be equal to this length. The pressure here would be equal to this length and this length. But this expression here is saying that the pressure change in the y direction is going to be different from that. And it would suggest that if it's accelerating and this is not equal to 0, then the pressure on the base, I guess, would be this amount would have a slope to it. And this would be dp dy bad y equals minus density of water times acceleration in the y direction. So it's negative. And so I guess if we wanted to draw this, this would just be dp dy. And I guess it would be more proper to, I suppose, draw it this way, right? Because dy is yeah. So this is, if this is positive, this is a negative gradient, right? In this quadrant, this is a positive gradient. And in this quadrant, this is a negative gradient, minus VE, right? So these are the geometries. Yes?
So just to clarify, the equation on the sides there that says P equals PGH, is that pressure equals density times GH?
Times gravity times the depth of that point.
Okay.
So this would be, in this particular case at the bottom, this would be H. Okay. So, but that's not the most interesting system. The more interesting system would be the open system, which is our bus, glass. So, and this is the same system as we had before. Y and Z. And so what we think is going to happen, because we've just seen it, is that if we accelerate to one side, then maybe this free surface is going to change. And so what we could do is we could take this relationship, and we could write that the change in pressure that we get, we know that as we go down in the fluid or across in the fluid, there's some pressure change. So we could write the change in pressure as a function of, let me write 3 of these out with a gap between them, and you'll see where we're going. So we could write the change in pressure that results from accelerating across the system, and this is going to be our acceleration. Positive acceleration in the y direction is this. So why don't we multiply this term by 1, this term by 1, and this term by 1, right? You all agree that dz is just 1. And so what we'd like to do is we could like to say that on this surface, the pressure acting is atmospheric, here. On this surface, when it's static, everywhere on this surface is atmospheric. You agree, right? That's what we feel. Likewise, on this surface, once it becomes tilted over, it would still be equal to atmospheric. But we can now define this as a function of these pressures that we define here. So we have a magnitude here, And we have a magnitude here that we can substitute. And let's say that going into the page, the planar inclination is horizontal, so dp dx would be, by definition, 0. There'd be no change. And so also, since the pressure here, and the pressure here, and the pressure here, and the pressure here are the same, we could set those to be equal to 0. So we have this. And if we substitute these two values, then we'd have minus density times acceleration in the y direction, which is this term, minus density times gravity plus acceleration in the z direction. So all I'm doing is I'm substituting these two values we have here, setting them equal to 0. I guess there's a dy that I missed out here. Why don't I put it in red? And a dz. And then we should be able to rearrange this, if my math's not horrible, by gathering the terms for dz dy is equal to minus. So this is just this equation. So the idea is that now, on this surface here, we have dy, and we have an elevation dz. So it gives us the inclination of that surface. So all we've done is we've used this full expression here, where we now accommodate these terms. If we look at these equations for x, y, and z, and we simplify them, we get the pressure change with y, the pressure change with z, which would give us how the pressures change in this closed body. But, bless you, but more interesting for this, we're interested in seeing what happens to the slope of this surface as we accelerate across the room with a tank or a bus window that has water between it. And so this is a standard result. It's plotted for you up here in x, but this is just y. So dy, just split them out. And what it allows you to do is that if you know from our bus that's going down the road, I don't know what it was, it looked like it was maybe 1 to 4, I don't know, for the inclination of this. Then this is dz, this is dy. So this becomes 1 over 4 equals ay over g plus az. G always acts downwards, as in this expression here, right? Gravity always acts in the negative z direction in our coordinate system. But the acceleration that we're adding to this, so az, acceleration in z would be going up in an elevator or going down in an elevator on top of gravity, which is always acting. And so in this particular case, if the bus is running along the road horizontally, then by definition, the acceleration in the z direction is what? 0, right? Just going horizontally. So this is 0. And as a result of this, the acceleration in the y direction would equal 9.81 meters a second squared over 4. Just this term here. So you have an accelerometer in your bus. Yes.
Where did the negative sign go from that top equation?
Yeah, the negative sign is gone because this is so to go from here to here, you have to go negative y, positive z. So this is in this coordinate system. That's a good question. In this coordinate system, positive y and positive z. This is a positive gradient. This is a negative gradient. That's exactly this is. Yeah, good question. Okay, that's it. So you can tell exactly what the bus is doing that we looked at just by looking at that, right? That might be a good thing to understand. Okay? Questions? Okay. All right, so the other thing that we can do, which gets a bit more complicated, is we can also look at rotating fluids. And so maybe I'll resort to my notes. So this is the explanation of all this. Here's the expression. No examples. Oh, I guess a couple of other things we could talk about, which are worthwhile talking about. And that is that if we have this open tank, so this is your bottle that you have in your hand in the elevator. dP/dz. So we know that what happens if you had your aquarium in the elevator and you decide to go up at some acceleration az, then you'd expect that the pressure distribution with depth, dP/dz, in your container as you're moving upwards would be exactly this magnitude here. Minus rho g plus az. G always acts downwards, and so is always positive. This is always 9.81. But az has direction. Acceleration in the z direction has direction as well as magnitude. Accelerate upwards, this would be positive because it's in the direction of the z coordinate system. Positive direction. And if it's downwards, it would be negative. So in other words, if you're going upwards, if this in a static tank is this, so if this is static, if this is az upwards, which is positive, where's my line go? And if this is accelerating downwards, just according to this equation here, right? And so it tells you what you kind of know. You're holding something in your hand. If you're holding a weight in your hand, a dumbbell, the elevator accelerates, not just constant velocity. The acceleration phase feels heavier. And the representation of that here is that the addition of an extra acceleration on addition to gravity makes it feel heavier, so you have to apply more force to keep it up. If you're going down, it feels lighter. And this equation tells you that if you're accelerating down at 9.81 meters per second, exactly countering gravity, then the magnitude of this distribution would be, you'd be weightless. It'd be the same as going over in the vomit comet, right, as NASA calls it. This plane that does a parabolic arc, so you can be weightless, floating around for a few seconds before, I suppose, you hit the deck or hit the ceiling. I'm not sure which, but I'm sure they do it to moderate that. Yeah.
Just confirm, does the RE, remember the RE that you wrote next to the AZ that represent the gradient?
Say again, what?
The RE, every
This?
yes.
VE, positive. Last two, I explained to this before, right? Positive is my shorthand. VE. Okay. Yeah. So I don't mean to confuse you or berate you. I know that from the past, people went through 10 classes and said, what is hell's VE? And then it's easy for me to tell you once someone asks. Yeah, so it's just positive. So accelerations have both magnitude and direction. The coordinate system that we use is like this. Y or X and Z. These are the positive directions. And that's our chosen coordinate system, X, Y, Z. Okay? So yeah, so in other words, you're weightless. Your blood in your body would not coagulate in your feet. It would just be free-flowing. And I guess if you're weightless in space, I guess there's all kinds of physiological issues about maybe pumping. I guess you're kind of self-contained, so your heart would work just as well. But I guess there's lots of physiological things with no stress on exercising muscles and atrophying of muscles, etc. Okay. Good? Fine. So linear accelerations are definitely on the test, and it definitely uses a prior question. I'm not trying to be smart. I'm trying to actually be helpful. I want you to do well. Nothing worse than coming to class on the Monday after midterms and looking at glum faces. I'd much rather look at happy faces who've done so well that they're ecstatic that they don't want to come to class because they're sleeping in and taking a day off because they've been working so hard. So I don't mean to be glib and flip. So this is all documented here. The other thing that we could think about and maybe talk in broader terms, which isn't on the test, as you'll see as you look through the review notes. If you think I'm trying to trick you on the review notes, by the way, look at prior reviews and compare them with the prior tests, and you'll see that absolutely everything you need on that review equation sheet you have to do the test. Doesn't solve all your problems, but it certainly is there. The other oxymoronic case is of accelerating fluids, rotationally accelerating. And this is a bit more esoteric, but the idea is this. You go to the fun fair, you go on the wall of death where you get spun around and they drop the floor from underneath you and you're stuck centripetally on this wall that's going around. That's really not so different from taking a fluid and rotating a can of beer around its central axis at some rotational speed. And so the other twist for this is that if it's going at a single rotational speed, say 1 revolution per second, then that is an angular acceleration, because acceleration is both direction and magnitude, as we just talked about. We're interested in the magnitude of it changing as you go across the room, but not the direction. In rotational acceleration, it's flipped. So the rotation speed of a particle that would be on the lip of the can that's going around and round would be 1 meter a second or 1 revolution per second, depending on how you're measuring it. But because as it's going at one location parallel to so this is the rim of the can, the direction of this motion is parallel to that, but to get to the next motion, it's changing direction. So it's going at the same speed, the velocity is not, the speed is the same, but the direction of that motion is changing as it goes around the can. Right? If I'm the can, it's changing direction because it's going all around the same, tracking with the machine. Good. A bit of theatrics, a thespian, no doubt. So you can get the equations for the fluid just like the equations we had for linear motion, and they look a little different. They look like this. This magnitude omega squared is the angular velocity. It's in radians per second. And so V theta, bless you, equals omega r or V theta over R is equal to omega. So if you have a radius equal to 1 and you have a velocity V theta which is 2 pi r per second, then if you divide 2 pi r per second by r, this equation, you get 2 pi radians a second. So that's where it comes from. So you can always convert into rotations per second, revolutions per second, but let's not worry about that here. So the idea is we can do exactly the same thing as before. So we can take these equations, take them on trust. It's the same as taking a piece of string and putting a weight on it and spinning it around your head. The force that you have to apply to that to keep it pulled in is the same as Newton's second law, but in angular coordinates. Bless you. And we can do exactly the same as we did before. We can take these expressions for dp dr, dp d theta, and dp dz. And we can try and figure out what the arc of this surface is that builds up as you start spinning it. And so you notice that this one is just that the pressure changes with depth according to the unit weight. So for instance, if the height of this surface at the edge of this container went up, then the pressure that's acting here would just be equal to P is equal to rho GH, and H would just be the height of this thing here. Right? That's what this is saying. It's no different from being in a static fluid. Happens to being flung around here, but it's no different that the pressure here is exactly the same as the height of water above it. It would be the same at this point. It would be the height of water above it. This says that as you go around, so theta is this coordinate system as you go around. And so all that's saying is that the pressure change as you go around at a particular radius doesn't change anywhere in the fluid. So if you go around at this depth here, and you come across here, and you keep on going around, all it's saying is that the pressure as you go in this circuit remains the same. And it kind of makes sense that that should be the case, because if you think about it, if you think about the location of this surface here, if you drew a contour around the inside of this can, it can't have a discontinuity where it ends up higher at some location and then has to drop down. It has to be continuous. So that's all that's saying. It's saying as you go around an angle, the pressure is always the same at any given elevation, any given point within this container. If you have this point at some radius here, it'll track at a smaller radius. And this is the one that means that it gets flung out to the side and causes this distribution of elevation. So not to belabor the derivation, let's just think we're doing it as before. Remember what we said was we think that if we have a surface, which now is a curved surface, that we can write that the pressure change across this is equal to the pressure change in each of the three coordinate systems. And then we can just multiply those by 1 individually. We do that exactly again. Pressure multiplied by 1, pressure multiplied by 1, pressure multiplied by 1. Throw this one away. This is the only interesting one that we have here, which we would substitute down here. And if we do that, then we get a standard result. And the standard result is this, that the elevation of this surface, well, that's not bad, is dr dz. So we're interested to know what this curvature looks like, and we have it dz dr, I guess. So it's the opposite of those. So we have an ability to get this. We end up with this equation. So this is a standard result. If we want to integrate it, we can do just as we did before. So we could divide it up to get dz and dr on the same side, just by dr, and integrate it. And you get this expression here. And again, you end up with a standard result. And this standard result is that the elevation changes as a function of the rotational velocity squared, gravity, and the distance from the rotation point also squared, plus some constant that we're left with. And so if we wanted to, we could solve for exactly where we are on this by writing this expression at some location. So for instance, if we wanted to calculate what the height was at z1, and we knew that at z0 was h, then we could write z0, we know the rotation speed, we know gravity, we know that the radius is 0. And so we know that the value of z0, let's say it's 1 meter. We'd know that the value of 0 would be 1 meter. So we'd know that the constant equals 1 meter. Has to be meters to be dimensionally consistent. And then we'd come back and then we'd calculate this. Do we get rid of this? Oops. I set it up so it only remembers the eraser once. And so now we'd want to get z1. We'd know the rotation speed we're going at. We'd know gravity. We'd know that the location of z1 is at some radius r equals 3 meters. We know that this constant is equal to 1 meter. And since we know this and know this, we can calculate what this is. That's it. So, and you can solve some problems doing that, which you don't need to because you don't have a question on it on your test. Okay, so same theme though, same thing. Trying to find out the curvature of the surface. It doesn't end up being a linear one, so we have to deal with it by solving for this constant and then going for it. And I guess the other thing that I didn't mention is that when this occurs, the other concept I guess you have to know is that conservation of mass means that this has to be the midpoint, right, of this tank. Because half of it's going down by this amount and the other half's going up by this amount. So the slope and the absolute height of this location have to be around this fulcrum, if you like. And I guess we'd also know that if you had to calculate what the pressure was at the back, this would just be equal to P equals rho g h, acting on the back. There have been questions asking what's the net resultant force acting on the back in the past. So, don't know. Okay, questions? All right. So we talked about these equations today. It's not in waste. We will rely on these now. So we finished talking about fluid statics, the fact that we can get pressure at a point as a result of knowing the fluids above it. We can also get the pressures by looking at the accelerations. Now we'll talk about Bernoulli's equation, where we have fluid dynamics, moving fluids. And we can actually use these expressions to be able to move, to look at that. So we'll deal with that next time. All right. That's all I got. Thanks very much.
Thank you.
You're welcome.